In the previous two classes, we have covered the Fourier series, which is given by when ft plus t is ft, f small t, and t is called period. Then ft is given by a0 plus n equal to 1 to infinite an cosine 2 pi n t over t plus bn sine 2 pi n t over t, where a0 is 1 over t from minus t over half to t over half to ft tt. An is equal to 2 over t minus t over 2 t over 2 ft cosine 2 pi n t over big T dt, and bn is equal to 2 over big T minus t over t to t over t ft sine 2 pi n t over t dt. There is a way to represent these three different coefficients into single function using the Euler formula that we have learned. So we have Euler's formula. Exponential I theta is cosine theta plus I sine theta. So cosine theta can be written as exponential I theta plus exponential minus I theta over 2, and sine theta is given by exponential I theta minus exponential minus I theta over 2I. So the Fourier series can be written as follows: a0 plus n equal to 1 to infinite an. We use Euler's formula to represent cosine 2 pi n t over 2 big T. So exponential I 2 pi n t over big T plus exponential minus I 2 pi n t over big T plus bn over 2I exponential I 2 pi n t over t minus exponential minus I 2 pi n t over t. So we can combine them together as a0 plus n equal to 1 to infinite an over 2 plus 2I over bn exponential I 2 pi n t over big T plus n equal to 1 to infinite an over 2 minus bn over 2I exponential minus I t over 2 pi n t. So we can set an over 2 plus bn over 2I is actually 2 over an minus ibn as a single coefficient cn, and an over 2 minus 2I over bn is actually an plus ibn over 2, which is same as cn over complex conjugate. Then ft can be written as a0 plus n equal to 1 to infinite cn exponential t over an, this is actually minus something is wrong with me. Probably I need the caffeine. 2 pi I n t over big T plus n equal to 1 to infinite Cn complex conjugate exponential minus 2 pi I n t. So for the second term, if we change n equal to minus m, we can have the following: a 0 plus n equal to 1 to infinite Cn exponential 2 pi I n t plus m equal to minus infinity to minus 1 C minus m complex conjugate exponential t over 2 pi I m t. Let's take a look. Cn is given by 1 over 2 an minus I over 2 pn, which is actually 1 over 2 over big T minus t over 2 ft cosine t over 2 pi I and t tt minus 1 over 2 over t I times minus 2 over 2 to 2 over 2 ft sine 2 pi I n over big T tt, which is written as 1 over t minus 1 over 2 to 2 over 2 ft cosine 2 pi n. There's no I. I think there's no I. I think I should change everything here. Oh, so actually 2 pi I n t minus 2 pi I n t exponential I 2 pi n t minus I 2 pi n t. But there is no I here, so I probably still need the caffeine. 2 pi n cosine t over 2 pi n t minus I sine 2 pi n t over t tt. And this is nothing but exponential minus I t over 2 pi n t. So Cn can be written as 1 over t minus t over 2 ft exponential minus I 2 pi n t over big T tt. When n is equal to 0, C0 is actually 1 over t minus t over 2 ft dt is same as a0. On the other hand, Cn to the complex conjugate is 1 over t over t ft exponential I t over 2 pi n t dt for ft real. So this is basically c to the minus n, or c to the minus n complex conjugate is Cn. So as a result, ft is written as C0 plus n equal to 1 to infinite Cn exponential T2I 2 pi nt plus m equal to minus infinity to minus 1 Cm exponential T over I 2 pi mt. So this can be combined together as n equal to minus infinity to infinite Cn exponential I t over 2 pi nt. So here we later change m into n. So when ft is periodic, we can represent into single complex Fourier series ft as n equal to minus infinity to infinity Cn exponential I t over 2 pi nt, and Cn is given by 1 over t minus infinity to infinity ft exponential minus I 2 pi nt over t dt. So let's take an example. Maybe we can break a few minutes. So let's consider the following example. This is ft, t, 2, 3, 4. In this case, we have a t equal to 4. So ft is given by 1, 0, and minus 3, minus 1. So in this case, ft plus 4 is ft. Then the complex Fourier series can be written as n equal to minus infinity to infinity Cn exponential I 4 2 pi nt, which is Cn exponential I 2 pi nt. So Cn is 1 over 4 minus 1 to 1 ft exponential minus 2 by pi nt, which is, but ft is equal to 1, so basically this is 1 over 4 minus 1 to 1 exponential minus I pi n over 2 t dt. So 1 over 4 minus I pi n over 2 exponential minus I pi n over 2t 1 to minus 1. Let me check if I can control it a little bit tinier than this one. This is 1 over 4, maybe too tiny, right? So I'll change it back. So 1 over 4 2 minus I pi n exponential minus pi n over 2 minus exponential I pi n over 2t minus I. Minus I pi n over become plus 2 exponential I pi over 2 n minus I pi n t over 2. So this is 1 over pi n sine n pi sorry, there isn't, because we have already put t equal to 1, so no t. So this is pi n minus pi n sine pi n over 2 sine pi n sine pi n. So Cn is 1 over pi n sine 2 over pi n. When n goes to 0, pi n over 1 sine pi n over 2 becomes, we divide by 2, 1 over 2 become 1 over 2, which is a C0. Ft is given by n equal to minus infinity to infinity 1 over pi n sine pi n over 2 exponential 2 over I pi n t. Perhaps I can give you the following example as homework. You can do it at home, such that one minus 1 so Ft t is equal to minus 1 to t, and Ft plus 2 is Ft. You can do this as homework. So as a special case, so in summary, complex Fourier series. Complex Fourier series is defined as Ft, and Ft plus big T is Ft. Then we have Ft can be represented by complex with a single coefficient, Cn exponential I t over 2 pi nt and Cn is given by 1 over t to infinite, not infinite, sorry about that, minus t over 2 ft exponential minus I 2 pi nt over big T dt. And I have to write clearly that this is 2 pi nt over big T. So as a special case, we can think of the function, non-periodic function. So, for example, we can think of arbitrary function as a periodic function with period t become infinite, right? So based on this idea, let's consider the complex Fourier series where t becomes infinite. So consider the complex Fourier series when t become infinite. So ft become represented as n equal to minus infinity to infinity Cn exponential I 2 pi n t over big T, and Cn is given by 1 over t minus t over 2 ft exponential minus I 2 pi n t over big T dt. From this, let's consider Tcn as 1 over t over 2 minus t over 2 ft exponential minus I 2 pi n t over big T dt, and consider omega n as defined as follows: 2 pi n over t. Then omega n plus 1 is equal to 2 pi over t n plus 1. Then omega n becomes omega n plus 1 minus omega n turns out to be 2 pi over t n plus 1 minus 2 pi over t over n is 2 pi over t. So when t become infinite, delta omega n becomes 0. So that means we can think Wn becomes, or as a continuous variable, as t become infinite, delta omega over 2 pi is delta n over t. Then summation over t because delta omega t also going to 0 as t become infinite. Then we can summation can be written as sum over delta n. And it becomes 1 over 2 pi delta omega. So we can regard 1 over t minus infinity. Let me see. So ft becomes over Cn exponential I 2 pi nt over big T, which can be written as 1 over T and Tcn exponential I t over 2 pi nt. So let's say Tcn is some tilde omega and 2 pi n over t is omega n. Then ft is 1 over infinite to infinite Cn exponential I 2 pi n t over big T can be written as 1 over t n equal to infinite minus infinite to infinite Tcn exponential I omega n t. It becomes delta n f tilde exponential I omega n t 1 over 2 pi minus infinity to infinity d omega f omega exponential I omega t. Then Tcn is f actual tilde omega is minus infinity to infinity ft exponential minus I omega t tt. So using this result, we just found out that any ft can be written as ft 1 over 2 pi minus infinity to infinity t omega f tilde omega x minus omega t, and f tilde omega is minus infinity to infinity ft exponential minus I omega t dt. And this is called the Fourier transform. It's called Fourier transform. we can check off this as the following. So ft 1 over 2 pi minus infinity to infinity d omega f tilde omega exponential I omega t is written as 2 pi minus infinity to infinity d omega. F tilde is actually minus infinity to infinity f t dash minus I omega t dash t t dash exponential I omega t. So it can be written as minus infinity to infinity minus 2 pi minus infinity to infinity exponential I omega t minus t prime t omega f t dash t t dash. So this part can be defined as a definition of a delta function, delta t minus t prime. This is called delta function. Delta function is defined as following: either infinite or 0, t equal to 0, t is not 0, and t delta t is equal to 1. That's the definition. This is a definition of delta function. The delta function. So, using this definition, think of the following. So, using this definition, minus infinity to infinity ft delta t dt is, since delta function has meaning for only when t is equal to 0, it becomes f0 delta t dt and f0 minus infinity to infinity delta t dt, and because this is 1, it becomes f0. So then we can think of the following: minus infinity to infinity ft prime delta t minus t prime dt prime is ft delta t minus t prime dt prime, and this is again 1, so it becomes ft. So let's consider this more specific example of a delta function that, let's say, delta t is defined as 1 over 2 from minus infinity to infinity exponential I omega t d omega. So let's take this as the following. Take a limit L goes to infinite, 1 over 2 pi minus L over L exponential I omega t d omega, and let's define as a GLT. Then GLT is 1 over 2 pi minus L over 2L exponential I omega t d omega is 2 pi it exponential I omega t from minus L to L is 1 over 2 pi it exponential itl minus itl is 1 over pi t over sine lt. So we multiply by L, divide by L, and we can write as the L over pi sine, LT over sine LT. When t goes to 0, of course GLT becomes L over pi. When sine LT is 0, t must be pi over L, L over plus minus 2 pi, plus minus, etc., etc. So we can this function as the following. Pi over L minus pi over L, 2 pi over L minus 2 pi over L. This is L over pi. So this function is something like this. There's a decreasing function. This area, this area 1/2 L over pi times 2 pi over L is equal to 1, right? So we can think that minus infinity to infinity GLT dt become 1. Also as L goes to infinity, GT goes to infinity. So GLT become delta function as L goes to infinite. So we can think as of Fourier transform as transform as an extension of complex Fourier series when the periodicity become infinite. So as an example, the following. It's a very simple example. Minus 1 to 1, 1. So ft is 1, t equal to minus 1 to 1, 0, otherwise. So in this case, Fourier transform of ft minus I omega t dt become minus 1 to 1 exponential minus I omega t dt is minus I omega exponential minus I omega t 1 to minus 1 is minus I omega exponential minus I omega minus I omega is 2 over omega sine omega. One of the useful examples ft is exponential minus at square. It's Gaussian function. When you integrate Gaussian from infinity to infinity, t square over dt is equal to pi over a. This is very important result, so probably it's better to remember the result. But also it is easy to prove. The proof is the following. Let's say I defined as minus infinity to infinity exponential minus x squared dx. I square can be defined as minus infinity to infinity a squared dx minus infinity to infinity a y squared dy minus infinity to infinity minus infinity to infinity exponential minus a square y square dx dy. And let's change this into polar coordinate. Such that x square plus y square is rho square, dx dy is rho d phi d rho. Then this whole integration becomes 0 to 2 pi, 0 to infinite, exponential minus a rho square, rho d phi is 2 pi times infinite to infinite, exponential minus a rho square, rho d rho. If rho square set as u, then du is 2 rho d rho. So this is become 2 pi 0 to infinite exponential minus au du over 2. This is pi from infinity to 0. Au du is pi over minus a exponential minus au 0 to infinity is pi over a. So a is becomes equal to pi over a, right? So when ft is given by exponential minus at square, its Fourier transform omega become minus infinity to infinity ft exponential minus omega t dt is minus infinity to infinity exponential minus at square minus omega t dt. It becomes minus infinity to infinity exponential minus a t square plus a over I omega t dt. We can t square a over I omega t. We can subtract 4a square. Continue. Sorry about that. The Shiri made a mistake. Plus omega square over 4a square dt. It becomes exponential minus 4a over omega square minus a t plus I omega over 2a square dt. This is another Gaussian. So it becomes exponential minus 4a omega square minus infinity plus I omega over 2t infinity plus I omega over 2t 2a exponential minus au square du. we have set u as t plus I omega over 2a, but infinite plus something is infinite again, so it becomes minus infinite, it becomes infinite, so it's become pi over a, square root of pi over a times exponential minus 4a over omega square. Another case when ft becomes tft, then its Fourier transform becomes tft exponential minus I omega t dt. It becomes I times d omega d. We can think of ft exponential minus omega t dt. So when we differentiate exponential minus I omega t by omega, we have minus it. So we can put I together. It becomes I d omega d f tilde omega. So we can generalize this to when minus infinity to infinity ft exponential minus I omega t dt is f tilde omega, then t to the n ft exponential I omega t dt becomes I d omega to the n f tilde omega. When the Fourier transform of ft is defined as minus infinity to infinity ft exponential minus I omega t dt, its complex conjugate is ft complex conjugate exponential I omega t dt. So absolute square of Fourier transform is f omega f tilde omega complex conjugate becomes ft exponential minus I omega t dt ft prime complex conjugate exponential I omega t prime dt prime becomes ft square exponential I omega t prime t t prime. So if we integrate this f tilde omega square d omega, then it becomes minus infinity to infinity minus infinity to infinity ft prime complex conjugate exponential I omega t prime t omega dt prime, and this becomes 2 pi delta t prime minus t then it becomes minus infinity to infinity ft complex conjugate t dt is infinity to infinity ft square dt. So we have the following formula. So absolute square of Fourier transform integrated from minus infinity to infinity is same as 2 pi times infinity, the original ft absolute square integrated over dt. This is called Parseval's theorem. And Parseval's theorem is very useful. For example, when ft is given by Gaussian function sorry about that, at square, then ft square is exponential minus 2at square, then ft square dt is minus infinity to infinity 2a t square dt is pi over 2a. On the other hand, Fourier transform, absolute square of the Fourier transform integrated over d omega becomes pi over a exponential minus 2a over omega square d omega becomes pi over a square root of 2a pi over 1. Is pi over square root of 2 pi over a, right? On the other hand, by the way, 2 pi times ft square dt is 2 pi times pi over 2a is pi times 2 pi over a. So they are the same, right? So we have the following. So we can say that square root of minus infinity to infinity f omega square d omega is always 2 pi minus infinity to infinity ft square dt. So let's consider the following example. Again, that ft is given by 1 to 0, t equal to minus 1 to 1, 0. Otherwise, then we have already obtained the result. Tilde omega is twice of sine omega over O. So f tilde omega square becomes 4 times omega square over sine square omega. So example is the following. Another example 2. Integration of this x square over sine square x dx. So you can actually apply the Parseval theorem here. So minus infinity to infinity. No. 0 to infinity x squared sine square x dx. You can transform it into 1 over 2 minus infinity to infinity x squared sine square x dx, or 1 over 2 minus infinity to infinity omega square sine square omega d omega becomes 1 over pi 8 times this omega square over 4 sine square omega d omega, and using Pascal theorem this becomes 1 over 8 times 2 pi minus infinity to infinity ft square dt, and it's actually pi over 4 minus 1 to 1 dt is pi over 2. So as a result, minus infinity to infinity, no, 0, 0 to x squared sine square x dx is pi over 2. Let's consider another example that when ft is t over 0, t is minus 1 to 1, otherwise, then this Fourier transform is 2i times t omega over sine omega. So it becomes two I times omega cosine omega minus omega square over sine omega. F tilde omega, absolute value square of a Fourier transform, is 4 times omega square cosine square omega minus omega cube 2 cosine omega sine omega plus omega to the 4 sine square omega. It's actually 4 divided by omega 4 omega cosine omega minus sine omega square. So if the question is the following, calculate this 0 to infinite x to the 4 x cosine x minus sine x square dx. Q is following. Then the Q becomes 1 over 2 minus infinity to infinity x to the 4 x cosine x minus sine x square dx is 1 over 2. You can transform into omega to the 4 omega cosine omega minus sine omega square d omega is again 1 over 8 to the minus infinity to infinity omega 4 omega cosine omega minus sine omega square d p omega, it becomes 8 times 2 pi to infinity to ft squared dt. This is Parseval's theorem. Then is pi over 4 minus 1 to 1 t squared dt is pi over 4 times 3 over 2 is pi over 6. So minus infinity to the x to the 4 x cosine x minus sine x square dx becomes pi over 6. Perhaps the following homework can be useful when ft becomes t squared and 0, t equal to minus 1 to 1 otherwise. So let's stop here today and continue next week. So next week will be the last class.